Welcome to another video explaining the universe using the particle model. Well, today's video is a continuation of showing how current varies with the speed of the G1, and this time I'm going to talk about to show you what it looks like in terms of a graph. But first, a message about our book. Yes, that's the logo of our book, the double apple. The large apple representing the physics that Isaac Newton started with, and the smaller apple, the work that David and I have done. You can get our book from Amazon. It's now available in hardcover for $41.99, paperback and full color for $34.99, and the ebook for $2.99. There's a simple link you can use to Amazon by using this link, tpm.thehilster.com. Well, I've been going through a list of words, and the words I've been really emphasizing for quite a while now are the equations. Last time I went through the calculations for the speed of the current. That's still the same. I haven't changed it. But now I'm going to graph the three sets of equations. One for standard model, one for the TPM without speed, and the one for TPM with speed. So some of this will be a repeat. But since it's been a while since I've made a video and my tests are not done, I thought I would interject this and present these as graphs. The G1 speed is really important. And this is the rule that I'm now following since I've understood this particular feature of the model. As the G1 current increases, the F2 force around the resistor increases, which increases the average speed of the G1s through the resistor. An increase of speed causes the G1s to pass through more easily. This theory helped explain the IV curve of the diode and the transistor. And conceptually, I haven't done any math or any calculations with the diode and the transistor, but conceptually, it explains the IV curves quite well. And in general, as the G1 enters an object, it speeds up, and as it leaves, it slows down. This is true of all objects, including my own body, as these particles pass through me. Now, here are the standard equations that you get taught, and here's the circuit I'm using, a battery, actually a variable power supply, a sensing resistor, a 1 ohm sensing resistor here, and another one here, and this is my resistor under test. And I'm going to see the effect on the voltage and current through that, voltage around and current through the resistor based on the speed. Now, in the standard equation, the current, the total current all the way around, and the current goes this way, is the voltage of the battery divided by the resistance of the three components. And you can measure the voltage across each one, and if you know the resistance, you can calculate the current, and they're all equal. There's a constant current at each level of the voltage. I'm going to be changing the voltage, but at each level, the current changes, but they all change together. And this is shown by this is for 5 volts when I set VB to 5 volts. And the resistor is a 4K resistor, and the current turns out to be 1.249 milliamps, and that's true for the first sense resistor, R1, and the second sense resistor. It's a flat line. Now, here's the TPM equations without speed. And yeah, this is the same circuit, except now the G1 particle goes around the other way. But the principle is still the same. But here are the equations. And the key point here is that the interaction factor is generally the same for resistors. I've been able to hold that pretty well constant. So I've been over these equations. I'm not here to re-explain them. It's just simple mathematics that the B1 is equal to B input minus the loss. And that's B1 is equal to the B input minus the loss. And I put these equations in a spreadsheet and I can calculate certain things. And this is a set of constants that I hope to find the actual value of each one, but for now I have to assume that VG1, the volts per G1 is some value, and that the interaction factor is equal to this number divided by VG1. But in this case, you lose G1, so there's less here and there's less here, so you expect to see it drop, which is the whole point. And sure enough, these still the same equations. I had to rig this differently to get the graph to show, because if I plotted these values, you get a virtual straight line except for this one. But I chose to plot these last three digits. That's this 7th, 8th, and 9th decimal digit we're talking about. That's how small these changes are. If I'm going to look for this, that's why I have to have an accurate meter to see if I can measure that down here. But you can see that as you go around the circuit from S1 to R1 to S2, it indeed does drop. In fact, this one drops even lower had I plotted all the 5 digits. So first one, standard straight line. TPM without speed, it's a continuous drop. Now here are the equations without speed, and here I introduce the speed factor, and the speed factor affects the interaction factor, does not affect S1, R1, and S4. The resistor is not changing. It's physically the same. My tests are going to be all at standard temperature and pressure, and I'm going to keep the current low so the components don't warm up and change. I'm taking precautions this way. So the speed factor, SF, is a factor that which will reduce the number of ones lost and let more through. Interesting, and that's true for all the resistors, even though this is a 1 ohm sense resistor, and the 1 ohm sense resistor here, that should be S2. They're all affected. So this speed factor affects how easily it hits or flows through, not the resistor value. The speed factor, I went over this in my last video. This is based on the M2 mass of the resistor or the sense resistor, and plus the number going through it. And this will slowly reduce let more through and reduce the number lost. If you reduce the number lost, you're reducing the voltage. If you reduce the voltage, the current drops. And this is the curve. Now this time, in order to show it more clearly, these are the same equations. This red line I added into the one for the here is the 1.249. That's the standard line. And look what happens with this from the spreadsheet. It's very high here. This is a big change, 1.26 milliamps. And when it gets here, it goes lower. Well, the graph in Microsoft spreadsheet the numbers are so close that you don't, that little blue line is right on the red line. I rigged it because literally the value is lower. It's just that the graphing technique of the spreadsheet doesn't allow you to visualize it. So I rigged it and pulled that down to show that it is in fact less than the standard at this point for R1, and then it goes back up. This is quite amazing. A 4K resistor, a small deviation being lower in a 4K resistor sets up a much higher value of current for the S1. And not only you would expect this to go down and down again, but it doesn't, it goes up. And that's because the average value for A, B, C are very, very close. So it starts out giving the first resistor many more G1s than normal. The number of G1s into that S1 resistor is equivalently shown here. Now it gets more G1s. Here it gets a few, but this is a 4K resistor. It's less, but and so these two, and then because that number A, B, and C don't change a lot, you're back up here. Hard to explain, but this is exactly what I'm expecting to have happen. And I went through this whole what is the G, and I'm guessing at this. The extreme value that you just saw for S1 and S2 in that previous chart is primarily based on my guess as to what the M2 mass of the R1 resistor and the S1, S2 resistor are. And chances are I'm way off. When I do some measurements, hopefully I'll find out what that number may be, but we'll have to see until I get the test done. Okay. Just as the TPM equation with speed again here, but this is a comment about the dropping of, I said that verbally just a minute ago, that the resistor value doesn't change. So if the voltage drops, which is what I expect it to do, then the current drops. That's that's all that slide was about. So I'm going to do some measurements, but I'm not going to do 3 measurements on the same circuit. I'm going to do one set of measurements on one circuit for each value of voltage, 5, 10, 15, 20, 25, and 30 volts. So my results may show me this. This is for the TPM with no speed up, or it may show it flat, or it may show this kind of a curve. So my one measurement is either going to match each one of these, or it might be some combination of these two or whatever. I don't know. That's why you do the measurements. I'll make my prediction. This is something I think I've seen. I've seen how the G1 particles increase because of certain factors, especially on the ones when I did the experiment almost 3 years ago. I took the large and small resistor and flipped their position, and you get a different number of G1s flowing, and I'm expecting that. I'm expecting the resistor to have the speed to have an effect on the current, just like it has an effect on the diode and the transistor. That's why I'm fairly confident that it'll be this one or close to it. And I'm going to use 5, 10, 15, 20, 25 volts. Each step will give you its own set of curves. A higher voltage should give higher current. The current will literally goes up, but not as much because the speed will bring it down a little bit. So I hope to be able to show that as you change this, you get this effect. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle. Thank you for your attention.